Welcome to today's Explainer. We're jumping right into one of the absolute powerhouses of the universe, Seyfert Galaxies. Today, we're going to explore exactly what these incredible structures are, how they actually work, and why they might just hold the key to understanding the evolution of the entire cosmos.
So picture this. You've got an engine sitting right at the core of a galaxy, and it's burning so intensely that it rivals, or maybe even totally outshines, the light of the billions of stars surrounding it. I mean, how is that even possible? What kind of physics can generate that sheer amount of energy in such a tightly packed space? Well, that's the ultimate puzzle of the active galactic nucleus, and Seyfert Galaxies are hands down our best window into figuring it out.
We're taking a bit of a zoom-in, zoom-out journey today. We'll kick things off with the discovery of Seyfert Galaxies, then dive inside the central engine and explore the unified AGN model. After that, we'll zoom back out to compare Seyfert's versus other active galaxies, look at their role as neutrinos and cosmic accelerators, and wrap up with the future of astrophysics. Section 1, Discovery of Seyfert Galaxies. Let's start with how humanity actually first noticed these things.
It definitely wasn't an overnight revelation. Back in 1908, Edward Pfaff noticed these weird, unusually bright emission lines in what they called a spiral nebula, specifically NGC 1068. Fast forward to 1926, and Edwin Hubble confirms, yep, these are extragalactic objects. But the real game changer hit in 1943. American astronomer Carl Keenan Seyfert published this massive seminal paper identifying a completely distinct class of spiral galaxies. He realized they had these incredibly bright, star-like nuclei pumping out broad, high-excitation emission lines. They were rightfully named after him, and it totally shifted our understanding of active galaxies. And then, decades later, in 1983, Antonucci and Miller would make another huge leap. But we'll get to that in a minute.
What's really wild is that Seyfert Galaxies aren't even that rare. They account for about 10% of all galaxies out there. And importantly, they're typically spiral or barred spiral galaxies, just like our own Milky Way. Think about that. 1 in 10 spiral galaxies is harboring this incredibly intense luminous core. Section 2, Inside the Central Engine. Let's zoom right in and dissect the actual mechanics powering these beasts. To understand what's generating all this light, we have to talk about the Eddington limit. Think of it like a cosmic tug-of-war. When an object blasts out massive amounts of radiation, that light actually exerts an outward pressure. If the object doesn't have enough mass, its own radiation will literally blow it apart. So the extreme luminosities we're seeing in Seyfert cores require an insane amount of mass just to combat that radiation pressure and hold the whole thing together. And that strongly points to one culprit, a supermassive black hole. And we aren't talking about your run-of-the-mill black holes here. These central engines are crammed into a hypercompact space of less than 100 parsecs, but they contain a supermassive black hole weighing anywhere from 1 million to 1 billion times the mass of our sun. As gas and dust fall toward this absolute behemoth, gravitational energy gets converted into electromagnetic radiation. This accretion process is staggeringly efficient. It converts roughly 10% of the rest mass energy into pure radiation. That's far more efficient than even nuclear fusion. Structurally, you can think of it kind of like a giant Russian nesting doll. At the dead center, you've got the supermassive black hole. Right around it is this violently glowing accretion disk. Just outside of that is the broadline region, or BLR, where high-density gas clouds are whipping around at just mind-bending speeds of 1 to 5,000 kilometers per second. Further out, wrapping around the equator like a thick, obscuring donut, is a cloud of dust we call the torus. And finally, extending much further out into the host galaxy is the narrow line region, or NLR, where lower density gas is moving at a much slower 500 to 1,000 kilometers per second. Section 3, the unified AGN model. Now, this complex anatomy leads us to a massive aha moment for astrophysics. For the longest time, astronomers had a classification problem. When they looked at Seyfert Type 1 galaxies, they saw both narrow and incredibly broad emission lines, meaning they could see the slow gas and the superfast gas. But when they looked at Seyfert Type 2 galaxies, those broad lines from the fast-moving gas were just gone. They only saw the narrow lines. For decades, everyone was scratching their heads. Were these just fundamentally, completely different types of engines? As it turns out, absolutely not. The unified paradigm of active galactic nuclei elegantly solves the whole thing. It turns out Type 1 and Type 2 Seyferts harbor the exact same supermassive black hole engine. The difference? Purely a trick of perspective. Remember that dusty torus donut we just talked about? If we're looking at the galaxy face-on, peering right down the hole of the donut, we see the fast gas near the black hole. That's a type 1. But if we view it edge-on, the dusty torus physically blocks our view of that inner fast gas, so we only see the slower gas further out. Boom, that's a type 2. And this was brilliantly proven in 1983 when Antonucci and Miller caught polarized light bouncing off the dust in a type 2 galaxy and actually saw the hidden broadlines reflected right back at us.
Section 4. Seyferts versus other active galaxies. Let's zoom out for a second and see where Seyferts fit into the whole cosmic zoo of active galactic nuclei.
So, looking at the wider taxonomy, you've got quasars, which are essentially the older, hyperluminous cousins of Seyferts. They're so blindingly bright they completely overwhelm their host galaxies. Then you have radiogalaxies, which live in these giant ellipticals and shoot out massive, radio-loud jets millions of light years across. And you've got blazars, where that massive relativistic jet just so happens to be pointing directly down the barrel at Earth. But Seyferts, they're special. They have somewhat lower luminosity, meaning they don't completely blind our telescopes. We can actually see the spiral host galaxy around the central engine, which makes them the absolute perfect laboratories for studying how a black hole interacts with its home galaxy.
But because we can see the host galaxy, astronomers need a reliable way to tell if the glowing gas they're looking at is powered by a black hole or if it's just normal star formation. So they use diagnostic graphs, like the BPT diagram, to basically read the invisible. By comparing specific ratios of emission lines, stuff like oxygen and nitrogen compared to hydrogen, they can neatly separate the high-energy, high-ionization signature of a Seyfert black hole from a normal star-forming HII region, or even from a lower-energy liner galaxy. It's literally a precise chemical fingerprint of black hole activity. Section 5. Neutrinos and cosmic accelerators. Recently, Seyferts have unexpectedly stolen the spotlight in the brand new field of multi-messenger astronomy. For decades, the consensus was that only the most extreme jet-firing AGNs, like blazars, were powerful enough cosmic accelerators to produce high-energy neutrinos. But get this, data from the Ice Cube Neutrino Observatory down in the ice of Antarctica completely rewrote that assumption. It proves that Seyfert galaxies, which are mostly radio-quiet and completely lack those massive jets, are actually prominent cosmic accelerators themselves. When we map out the relationship between distance and neutrino expectations in the southern sky, it confirms that nearby Seyfert galaxies, especially heavily obscured ones, like NGC 1068, are blasting these elusive ghost particles right at us. Even without massive jets, the extreme environments around their central black holes are accelerating cosmic rays to ultra-high energies, sending neutrinos straight through the universe and into our detectors. It's a real game changer. Section 6. The future of astrophysics. So, with all this incredible machinery operating inside 10% of the spiral galaxies in the universe, where do we go from here? Honestly, we are entering a golden age of observation. With the James Webb Space Telescope capturing ultra-high-resolution infrared data, often teamed up with powerful X-ray observations from Chandra and upcoming observatories like Athena, we are finally untangling that blinding nuclear light from the host galaxy's stars and looking ahead to monster facilities like the Extremely Large Telescope and the Square Kilometer Array. Researchers are hoping to map out the intimate relationship between a galaxy's mass and the mass of the black hole at its heart. We want to understand how AGN feedback drives galaxy evolution and finally unlock the secret of how supermassive black holes grew so impossibly large, so early in the universe's history. As we wrap up this explainer, we really have to wonder about our own cosmic backyard. We know Seyferts are mostly spiral galaxies, right? And we know they represent a phase where the central black hole is aggressively feeding. So is this violent, incredibly bright engine phase just a mandatory stepping stone in the evolution of galaxies? Did our own Milky Way, with its super quiet central black hole today, once shine as a brilliant Seyfert galaxy in its distant past? By studying these cosmic engines, we aren't just looking out into the void. We might literally be looking at a reflection of our own galaxy's history. Thanks for joining me on this deep dive, and as always, keep looking up.